welcome to the Masterclass on Advanced Propulsion. This photograph doesn't show propulsion at all, but it shows a flight hardware in test, in a plasma wind tower test, for which we use plasma sources that we derive from our self-developed high-power propulsion systems. So it's quasi dual use in a technical sense. Yeah? Okay, my content is, I will give an intro and a motivation, which starts with some definitions and thoughts for part of the propulsion program, electric propulsion. Then I will say some words on EP systems at RS. Likely I will skip the PPTs because this is sort of boring from the point of view of being advanced. But I will concentrate on self-feed MPD and applied feed MPD devices and on typhus, RAMEP. And then I will say some words on propulsion for missions in the solar system and beyond. Yeah, but we have to take this carefully because some of the concepts I'm showing are at the limit of the understanding in physics. I will say that by the time we reach the slides, because we have to be careful in taking everything what I'm saying sort of too serious. Yeah? Okay, space travel. Let's define this. Yeah. What is space travel? It's in principle all anthropogenic activities in space. Yeah? In other words, launch and access to space, operation of objects in vicinity to Earth, missions near Earth but outside its gravitational regime, travel within the solar system, and interstellar flight. Well, the green symbols signify that we're doing it. The red crosses say we don't do it at least on the level of manned missions, at least not currently. And the last red cross is saying we do not do interstellar flight. I guess you're all well aware of it. Okay. What's the resume? The resume is standing here. Up here we have the applications and the balance and what we're doing, and here it's saying what the propulsion characteristics do. Primarily there's a launch with chemical or high thrust systems that are energy limited, so we have a limited, what we call effective exhaust velocity CE. Energy limited means what we have available as an energy is given by the reaction enthalpy of the propellant as an upper limit, and we do not get more because there's no adds-on in energy. Yeah? If you burn hydrogen with oxygen, then you have the reaction enthalpy of hydrogen that is oxidizing as upper limit. And this defines or relates to the fact that the maximum theoretical values for chemical launches for the exhaust velocity are in the order of 5 kilometers a second, in atmosphere rather at 3.3 kilometers a second. No more. This is what we have. Then we have either impulsive orbit maneuvers applying low CE or unpulsed low thrust spiraling applying high CE systems, which is the world of what you would call the domain of electric space propulsion or advanced propulsion. Why is that? We will see this later when we look at these two primitive equations. The upper equation is a kinematic relation that somewhat relates what you could name acceleration in an integral dt in order to get a velocity gain. Firstly I name it velocity gain. Yeah? And the second is Tsiolkovsky's equation. Both equations are of the same importance, because if you relate everything to the Tsiolkovsky equation only, then this can mislead you to the aspect or to the issue saying the higher CE the better, because the higher CE is the lower my mass consumption for propellant is. This is wrong. It's wrong for several reasons. One reason is, we will learn this on the next slide, is if you increase CE more and more, then you suffer from the aspect of losing the acceleration and hence the thrust. So the best CE system that we have is a torch. But a torch does not have any thrust. This is what I mean. And this is lost as an information in the Tsiolkovsky equation. But you can win this back. I don't show this. But you can get this back when you present Tsiolkovsky's equation in another form, namely depending on the payload mass fraction. When you do that and easy peasy differentiate it against or towards the payload mass fraction, then you learn that there is an optimum CE in order to maximize the payload mass fraction. In other words, in reality, each mission has an optimum CE. Understood? This is very important. Yeah? Because many people, even colleagues of mine, are constantly telling you the higher CE the better. This is just wrong, okay? The delta V, of course, is of very high importance because delta V has become a sort of systematic approach from the point of view of guys doing mission analysis, because at the end of the day they optimize the mission with regards to the energy consumption, but what they deliver to you is a total delta V of the mission. In other words, the total sum of each fractional delta V done along the entire mission, in order to give you an info on the level of total delta V, in order to bridge you to, when you use Tsiolkovsky, to this mass ratio which somewhat dictates the amount of propellant you need. Yeah? So it's very important. So, and to confirm this, what I said before with the torch, when you lead these two equations together with some sorts, then you get this equation. Yeah? And this equation is saying acceleration times exhaust velocity of our thruster system is limited by alpha lim. Alpha is a mass-related, a mass-specific power. It's the mass-specific power primarily of the jet that is produced by the propulsion system, but secondarily it's the mass-related power of our power system. So the power unit system, including the solar arrays. Yeah, in other words, if we look at nowadays available technologies, then we're talking about typically solar arrays with a respective electronics, which is sometimes named power unit, and both of them somehow sum up in a certain value range of kilogram-related power. In other words, nowadays we are limited with alpha. So this means alpha is punishing this product. And this means if I want to employ a technology with high CE, think of Tsiolkovsky, then alpha lim is dictating that A is significantly reduced. In other words, high CE leads to a lower thrust with the given alpha, which is in turn limited by the technological feasibilities. With typically fairly high exhaust velocities, but the respectively available thrust levels are low. At least low as compared to typical chemical thermal systems as they are used with launchers. Understood? The other way around is to increase the thrust, but then to pay the price of losing CE. So this is given. The only way out would be to increase alpha lim. We'll see this later, yeah? What happens if we do that. Okay, just again for distinction, yeah? If we have a chemical system, we use the exothermal chemical reaction enthalpy in order to produce thrust and momentum for the propellant that leaves the nozzle or whatever we have as acceleration mechanism. While with electrical power, we insert electrical energy from outside to a potential propellant that can be even inert from the chemical point of view. So we have propulsion systems that can live with xenon or argon that are chemically, or well, they are noble gases, so chemically inert, but the message is that we introduce the energy from outside. So we are not anymore energy limited, but we are power limited. If we weren't power limited, we could even come up with thrust and CE levels that are far superior to what the chemical systems deliver, but we are. This is the situation. Maybe in a midterm future, and with midterm I mean at least some 10 decades, we may solve this issue, but not now. It's too early. Okay, how do we distinguish typologies of electric propulsion systems? In principle, we do it with a cupboard. When you are a student, you have to have a systematic way of thinking, and the classical systematic way of doing it is to distinguish between the different acceleration mechanisms that are applied to the propellant. That's the classical one where you use a nozzle. You see here IRS High Park, which is a high power arc jet in operation, and you see it's equipped with a nozzle, a geometric nozzle, like with the chemical thrusters or the chemical propulsion systems, and hence we call this electrothermal thrusters, which are arc jets and on top of this resistor jets of course as well. And they are sort of limited with regards to what you can produce as effective exhaust velocity. So high park achieved at 100 kilowatt yeah, which is fairly high, 20 kilometers a second. In other words, when you are in a typical area of 1 kilowatt, you are limited to 10 or 9 kilometers a second. The propellants are lightweight because the lightweight nature of the propellant supports the expansion process, or it supports the CP, the heat capacity. The lower the molar mass is, the higher the heat capacity is, and hence you have less problems in conveying the energy from internal energy to kinetic energy. Then the second group is what we call electromagnetic thrusters or magnetoplasma-dynamic thrusters. Yeah? I write here SF and AF, which stands for self-field and applied field MBD thrusters. SF means I'm making use of a self-induced magnetic field in the plasma that interacts with the charged particles and accelerates them. While AF MBD means I make use of an external magnetic field that interacts with the charged particles in the plasma and accelerates them. A much more complex process, by the way, as compared to SF. Next group is electrostatic thrusters, what the media typically name ion thrusters. And the biggest group out of them is the gridded ion thrusters, equipped with grid systems that accelerate the ions via the use of strong electric fields. So it's an electrostatic system. The third group is advanced thrusters that, for example, hybridize some of these acceleration mechanisms, but also do other things on the way how the power is coupled. For example, when you are inductive, or some people also like the term helicon, which I absolutely dislike because it's artificial. It does not exist. If you run an inductive system with charge separation, you have a helicon. This has been known to the Russians since the 1960s, but they would never ever call it helicon. Yeah? On the contrary, they even say we dislike it. Hybrid thrusters that hybridize certain aspects in terms of acceleration or in terms of power coupling, or more advanced systems like field reverse configurations or inertial electrostatic confinement systems. Okay, the application. In principle, we have to distinguish two applications. The first class is science. We're doing science. Apart from doing science in an Earth orbit or Earth vicinity, we're doing science sort of abroad, so more far away. And the key message is that for some groups of applications, sorry for the German, but I translate this delta V here is saying cometarian rendezvous, flight to sun, or interplanetary return missions or sample return missions. In other words, this delta V regime is somewhere larger or equal than 25 kilometers a second. Now when you stage a chemical thruster, first stage, second stage, third stage, and parameterize vary the CE of a potential third stage that is electric, then you learn that a certain group of missions, scratching landing missions on planets, but in particular sample return missions, is only possible with electric propulsion. It's just not doable when you do it purely chemical, because you cannot overwhelm the respective burden of the delta V. Okay, this is science. The other world is business. Business is when you earn money with EP. And there are some firms in the world that earn money with EP. For example, Aerojet in the United States is constantly selling arc-jet systems for secondary propulsion. Yeah? What is secondary propulsion? Secondary propulsion means I have a satellite in Earth vicinity, in orbit, and I have my typical disturbing accelerations in north, south, and east-west direction, and I have to keep the satellite in a certain square or cube. For example, a geostationary television satellite has to remain in a certain cube in order to cover the respective area on the Earth's surface, and this is done via propulsion systems. And nowadays the trend goes more and more towards electric propulsion systems because due to Tsiolkovsky's equation, they respectively need less propellant. So either you can reduce the mass and respectively the size of the satellite, or you leave mass as is and have more propellant and increase the lifetime of the satellite, and this is business. Yeah? There's one exception for primary propulsion currently, this is transfer. When you have orbital transfer from GTO to GEO, then the customer is typically, in Europe at least, typically dictating this has to be achieved within 6 months. The reason is evident. The first reason is the faster it is, the earlier the application will come in GEO. The second reason is the period of transfer is paying interest rates, is paying insurance, and so forth. So it's money. When I mean customer, I do not mean Airbus or one of the large system integrators. I mean, for example, firms like SES in Luxembourg. This is a typical requirement, 6 months for transfer. Yeah? And for the very heavy satellites, this even employs thrusters that have to come up with fairly high thrust levels rather than high CE levels. Okay? And this overview just shows some exemplary satellites as equipped with EP systems like here ion thrusters, arc jets, Hall ion thrusters, PPT and Hall thrusters, or PPT and combined Hall thrusters in principle from the Russians. And you see there's a significant number or group of satellites in orbit that are operational and that make use of EP in order to be at the right place, at the right position, and to guarantee a certain leveling of the lifetime aspect, which cannot be achieved comparably with cold gas systems or respective monoprop or chemical systems. Okay? What is IRS doing? This is known to most of you. We're doing this and this. And in principle you can say we're doing plasma propulsion. And this here is low power to medium power. So this is 100 watt with PPT. This is an arc jet with 1 kilowatt. And when you here draw a line, you enter to high power. High power means here, for example, High Park, which is a 100 kilowatt arc jet. Or self-feed MBDs that we operate at powers of up to 1 megawatt. Or most recently SX3, which is an applied field MBD that we qualified up to powers of 125 kilowatt. And in between there's Titus, which is a hybrid system, a series of an arc jet with an ICP, an inductively coupled stage. Okay? And the more advanced things are, here it says IEC, which is a technology coming from fusion, or fusion physicists, back in the 1950s from Hirsch and Hans Farnsworth, developed by Hirsch by the two guys. And what do? They collapse with 2 electrodes of plasma into the core. As it is collapsed, it is equipped with a fairly high energy density. And when you disturb the outer electrode adequately, you can achieve a jet leaving the core. And this jet presumably has a fairly high energy. Higher than, for example, the energies that we do expect from classical ion thrusters. So we can future high CE thruster. Then here, ABEP, air breathing electric propulsion. I guess this is very generic. I don't show more because this will be shown tomorrow by Francesco. And here, water-based propulsion, which I name secondary electric propulsion because we're making use of an electrolysis system to produce the propellants prior to burning them. It's a nice collaboration with Airbus. And mini PPTs that we currently develop in collaboration with ESA for CubeSats. This is what we're doing. Okay, I skip in my talk arc jets and I start with MBD thrusters. Now, what is the motivation for high power MBD thrusters? It's exactly the message I conveyed to you with the Tsiolkovsky equation that leads to the fact that for certain missions there are optimal CEs. And the classic way or classic scenario is heavy cargo missions, manned missions to Mars, or manned missions beyond. Typical analysis show that you need certain requirements fulfilled, but in particular when you look, for example, at manned missions to Mars, you end up in scenarios that always look similar to this. So typically they deliver the doublet, make use of several tens of Newton in thrust, and make use of some 3,000 seconds in specific impulse, which is another language for the exhaust velocities as it is divided by the Earth acceleration. And on top of this there's an efficiency value which is in an order of 45%. But this is mission analysis, and mission analysis hence telling us if I want to fly to Mars with electric propulsion, I need these parameters, and these parameters, as we will learn, can be fulfilled by MBDs. Okay, how does a self-field MBD work? Well, the principle is quite simple, but it's always like this. You have a principle and then people are saying, oh, it's this easy peasy. Yeah, but when you implement it, you're fighting for years. Okay, the easy peasy part is you have an anode system and a cathode system, and the current densities in a dimension of amps per square meter have to be that high that you engage a self-induction of a self-induced magnetic field that in turn interacts with the current density itself in order to produce respectively positive or constructive Lorentz force densities that accelerate the propellant in axial direction and towards the core of the jet, which is also positive, or positive contribution to the momentum the thruster has. In other words, we are using Lorentz forces to accelerate, and some simple derivation leads to a proportionality of the thrust against the second power of the current. In other words, you have to run self-field MBDs at extremely high current levels in order to have an adequately induced self-field that can interact with the plasma respectively. That's the key message. We developed a family of MBDs at IRS. Just to be very principled, we distinguish cylindrical from nozzle-equipped systems. This was done in order to assess the evidence of a thermal thrust due to the nozzle, for example. And we distinguish radiatively cooled and water-cooled anodes. This is very important for the arc physics. The so-called fall regions of the arc fully differ if you have hot anodes rather than cold anodes, and this feeds back even to the efficiency. But this is another story. And I run through these slides because it's not so important to see the diagrams, it's rather important to realize the values. Here you see typical thrusters in operation, you see the voltages and the respective currents, you see we have 15,000 amps. Steady state means over hours. And you see a typical history which is linear, which is a nice message, because when you are running an MBD, then you have to realize that only the charged particles visualize or feel the magnetic field. Hence you have to be fully ionized. Given that you were fully ionized, then this leads with some thoughts to a linear behavior of the voltage against the current. So seeing the linear behavior means you are in the right regime, operationally. But there's also this phenomenon where it increases further, which we call onset, which is a lack of charged particles near the anode, which cannot be really overcome. Maybe it can, but I don't tell you how. Okay? At the end, you see the key message, 15 Newton
as a thrust value together with an adequately high level for the specific impulse. So a cluster of these thrusters at an overall power of around 3.5 megawatt would fulfill typical manned mission requirements.
At a certain stage, we switch to what we call applied field thrusters. Direct your eyes to this, which is saying IEC RBIP concept. The strength of the IEC as an RBIP system is that you have a merge of the thruster with the mass collector, the intake. That's the strength. So if you are keen, you can start the development of that, because we do not have the resources, nor do we have the money for patenting it. Applications, RBIP, plasma thruster, fusion propulsion, because IEC, if you use the right choice of propellant, you can look at fusion relevant processes. So in the far future it might be fusion propulsion. So HEO and beyond. I want to explain why you can come up with the F equals 100 Newton and 3000 seconds, or 30 kilometers a second. The major message is that a manned mission to Mars has to be splitted. The reason is you have to maintain an adequate level of flexibility, because flexibility equals safety. What does this mean? Well, it's very simple. You have a group of astronauts flying to the Mars, and all of a sudden one critical technical system fails, and of course they would like to be able to return, otherwise they won't survive. And these interruption scenarios drive this doublet of thrust and exhaust velocity. Okay. Since the moon mission, Mars missions have become sort of realistic, at least in the mind of people. As I said, potential thrusters for such missions could be Titus. This is a video. You see, it's quite boring, but it must be boring. The videos have to be boring, because if they weren't boring, you would see things like sputtering from the electrodes, and this is bad. Electrode sputtering means you haven't overcome the physics of the electrodes, and hence you haven't overcome the aspect of lifetime. The same applies to applied field MBD. This is even worse, it's even more boring. It almost looks like a photograph, but it's a video. It should be a video. Let's think it's a video. Okay, and you have start windows every 26 months. This is due to the energy level you require or need for the mission. And you have different scenarios of durations. One duration is 3 years with a 1.5 years duration on Mars, or 1.5 to 2 years with a 30 to 60 days mission on the surface of Mars. This is what you can do. And these are reference missions that verify our analysis. And with impulsive, you of course do Hohmann transfer, the classical one. And with electrical, you come up with these parameters. You see, the AFMBD overcomes this with more than 35 kilometers a second and overcomes this with more than 50% efficiency. And for achieving the thrust, you have to cluster it. So a cluster of AFMBDs can do this mission. Split mission means at the end you have to use a group of spacecraft. One spacecraft brings the habitat and infrastructure elements to the surface. The second spacecraft brings propellant to the orbit. The third spacecraft brings a first group of astronauts to the surface. And you can interrupt. When you see that the habitat does not work out, you stop the whole thing. This is the flexibility I meant. Okay, let's come to the more advanced things. What is our curse? Our curse is the alpha equals F times CE times 1/2 issue, which I mentioned before. And this curse directly bridges to the philosophy of designing a spacecraft. Nowadays, the design of a spacecraft is mission related. A spacecraft that is designed can only do one certain mission, with certain exceptions. For example, Stardust was an exception. Stardust, the mothership of Stardust, was redirected to Dawn after it arrived at Earth in order to look at the crater that was produced by deep impact. But this is the only example I know, to be honest. Typically, a spacecraft can do only a certain mission. For example, a cometarian visit or a sample return mission. But it cannot do more. And this is a certain level of paradigm. And of course we would like to have another paradigm, namely that we design spacecraft that are flexible in their application. And this is only doable with high power thruster. Here it's saying high power thruster for interplanetary travel. What on earth does this Herdrich mean with that? Well, the point is, when you do continuous propulsion with EP, then you do, or Hohmann ellipse, when you do chemical propulsion with impulsion, you do something like this. And these transfers are energy optimized with regards to the applied thruster system. The message is to go away from this. When you do high thrust, then you can even analytically solve the equations. I don't show this, but it's doable. You can analytically, this branch here is not arbitrary. This branch is how it looks like in reality. When you have a high thrust transfer, this looks like this. And the solution is a set of two integrations that deliver distance depending on time, velocity depending on time, and so forth. And the point is, you can only achieve these thrust levels when you end up in systems that have the adequacy or the adequate thrust level, hence that overcome the alpha problem, which I mentioned before, and the alpha problem is solved via either assessing certain technologies that produce higher alpha. Do you know examples that produce higher alpha? Nuclear fission, I don't dare saying it, and nuclear fusion, for example. Or when you look at the limits of the currently available theoretical base of physics. This is another story. But I say some words on that. Okay, this is a mission scenario of a fusion propulsion system to Mars. And you see the curve, how it looks like. It's from SDK. We use SDK to verify our algebraic model, and we typically get deviations below 5%. So the algebraic model works. And you see, with these thrust levels and these exhaust velocities, we of course overcome the duration issue, leading to the fact that the whole mission back and forth lasts less than 50 days. The same happens, of course, if we make the thing bigger in volume, because volume means more thrust, then we do it in 33.8 days. Actually, don't laugh at me. There's a whole dissertation currently ongoing at IRS looking at the fusion propulsion concept. Emphasis on concept. I'm almost finished. I hope so. Anybody who doesn't love this shall leave the room. I can well imagine that a certain group of men sitting here doesn't dare saying that they look Star Trek or like looking Star Trek because they are married or have a girlfriend. But you know what I mean. I have lost the sound, that's a pity. Yeah, but you know the sound. Most of you guys know the sound, right? Also the women know the sound, right? Okay. And I start with the first bad thing, warp propulsion. I made some distances here. Yeah, Stuttgart Rust is my home place. It's a village in the south of Baden-Württemberg. It's 200 kilometers, 2.5 hours with the car. Light takes 1 millisecond. Earth mass is 75 million kilometers. It lasts longer than 6 months, what we have learned before. And light takes 4 minutes and 10 seconds. One way. Earth Proxima Centauri is 4.24 light years. It takes you, with typical propulsion systems, some 90,000 years to reach. And light takes 4.2 years. Earth Andromeda is 2.7 million light years. It takes you 58.333 billion years. And light takes 2.7 million years. And you know this guy with his special relativity theory. The major message is that materialistic particles cannot accelerate it beyond the speed of light because of this mass dilatation issue. But then he came up with the general relativity theory, and he did that by employing a four-dimensional space-time coordinate system. So he added time as the fourth coordinate on top of it. And the whole outcome is that the distortion of space is achieved due to the presence of mass, and that within the distortion of space where you are, or the distortion per se that produces the space in a non-Euclidean metric because everything is curved, that you can invest some thoughts. And the primary thought is that objects in here in two different relations can move against each other, could move against each other with relative velocity faster than light. But only in an argumentation that this does not contradict the theory. So this argumentation is very weak. The weakness is, it's just saying it does not contradict. Okay, then people have looked at it, and for example, Alcubierre and Van den Broek produced metrics, special metrics, in the space-time coordinate system that allow for this aspect to fly faster than light. This is reported in some quantum journals and whatsoever. But the generation of each of the known metrics to achieve this requires masses with negative energy density. And it's maybe one example where the mathematical tools dictate something which the physics may be neglecting, although you have to say that there are many rumors and statements on dark matter and so forth. By the way, apparently this issue is solved, because there are some guys that found the missing mass, additional mass in the form of gas masses in between the galaxies. There are some Nature publications on that. Let's assume we want to fly to the Centauri system with classical thrusters. We accelerate to travel speed, we fully consume the propellant, which is 10,000 tons. We pass with the speed of travel, and we have a robotic payload of 400 tons. Then Titus takes us 26,000 years, and we reach 0.02% of the speed of light. NERVA, which is a fusion thruster as developed by the United States in the late 60s and 70s in the last century, is a bit better, I think. It has a power of an order of 4 gigawatt, and the thrust is related to the mass of 29 big elephants. One thruster takes 48,000 years, and we reach 0.01% of the speed of light. Fusion concept at RS, one big elephant of thrust, 2 gigawatt, 3,800 years, 0.12% of the speed of light. I say yes, but I say no, because what I'm narrating here is concept. It's only concept. It's like fairy tales. Yeah? Some of you may know Daedalus. It's a primarily British concept with a thrust level of 192, big elephant. This is how people imagine how it could look like. One thruster takes 37 years and reaches 12% of C0, and this is the size. This is the last chapter. I want to show a hypothetical field-based propulsion. It's extremely doubtful. Burkhard Kato worked during the Second World War in an ammunition manufacturing plant, and he experienced a very severe accident. And he was quasi blind and handicapped with regards to his hands, and he stayed almost the rest of his life in bed. And what happened was all his theories were quasi-orally conveyed to his wife, and he wrote it down. And this was how his books were produced. What did he do? Well, he extended time, inverted comma, into 6 dimensions. And of course, when he adds 6 dimensions, this postulates 2 additional forces. Nowadays, we have many, many people that do the same. They postulate certain forces, they do measurements, they never verify it, and you know, it's all the same here. But it ends up in the postulation of a gravitophotometric force that can lift from a high magnetic flux with a rotating disk without propellant mass. I'm just saying where we are. And this leads to a force of 2,700 Newton, as for example published by Drescher and Heuser in AIAA 2003. But mind, this theory limits nowadays understanding in physics. A review is not yet performed. Consider this as considerations. It ends up in the fact that a trip to Mars can be done in 3.7 days. Let's summarize. EP systems and advanced EP systems at IRS. I showed the application in science and the business scenarios that are dominated by secondary propulsion aspects, with one exception, propelled transfer from GTO to GEO. This is also a business case. Then I switched to advanced propulsion that are typically aiming at advanced propellant acceleration, significant flexibility, for example with Titus, that can use almost any propellant in its second stage due to the absence of electrodes, and or increase of mass-specific power and energy density to solve the alpha lim times CE problem, and or new domains in physics that, however, have to be assessed in a very, very critical way. Be critical with that. Summary 2. This talk was given by me, but behind this there's a team of 10 to 12 people doing the work. The team is quite nicely networked. We have running NASA space ESA contracts, DLR contracts. We do a European Union DFG project with firms. We have collaboration contracts. We're just networking with Chinese entities, and they engage quite a lot of resources as we currently observe. In other words, it might be better to collaborate. And the other China, which is NCKU and Taiwan, typically we instrumentalize further collaboration firstly by student exchange, internships, PhD scholars. And there's this one which belongs to this cover, which is a seminar on project and strategic project management with the UPC, which we want to engage, and that's it. I'm done. Thank you.